Good morning, students. I am Dr. Suhas Janwarkar and going to teach you analytical chemistry. But before discussing anything, let me take this opportunity to welcome all of you to TY Basic Chemistry class. I am going to teach you analytical chemistry. In analytical chemistry, we will discuss the optical method, that is unit 3 of paper 4. Now, all optical methods are based on one law, that is Beer's-Lambert's law. Now, before discussing this Beer's-Lambert's law, we must understand what is the assumption of Beer's and Lambert's law. So, Beer's assumed that the absorbed media is made up of infinite number of successive layers having equal concentration, while Lambert's assumed that the absorbing media is made up of infinite number of successive layers having equal thickness. So, the Beer's statement is when monochromatic beam of radiation passes through absorbing media, equal fraction of incident light absorbed by successive layer of equal concentration. Now, in the diagram, we can see the absorbing media and the successive layer has been shown by red lines. I0 is the intensity of incident radiation and IT is the intensity of transmitted radiation. In the another diagram, the one layer is shown having the concentration, that is DC, and thickness, that is TL. Similarly, Lambert's law can be stated when monochromatic beam of radiation passes through absorbing media, equal fraction of incident light absorbed by successive layer of equal thickness. Now we will go for the derivation of Beer's-Lambert's law. As we have already discussed that the absorbing media is made up of successive layers and each layer absorbs equal fraction of incident light, and the fraction of incident light is given by di by I. So the mathematical equation will become minus di by I is directly proportional to this, where negative sign indicates the intensity of incident radiation goes on decreasing. The proportionality sign can be removed by substituting proportionality constant. So the equation will become minus di by I is equal to K1 dc. Integrating the equation on both sides, we get di by I ranging from I0 to IT is equal to minus K1 ranging from 0 to C dc. On solving this integration, we get ln of I ranging from I0 to IT is equal to minus K1 C ranging from 0 to C. So the above equation will become ln of IT by I0 is equal to minus K1 C. Similarly, we can derive the Lambert's law, which becomes ln of IT by I0 is equal to minus K1 L. Combining these two individual equations, we get Beer's-Lambert's law, and it becomes ln of IT by I0 is equal to minus K1 CL. So, if we convert this ln into log to the base 10, then we have to multiply the above equation by 2.303. So, the equation will become 2.303 log of I0 by IT is equal to KCL. By inverting the ratio of IT by I0, we convert the negative sign into positive sign. Since log of I0 by IT is equal to absorbance and K upon 2.303 is equal to epsilon, that is molar absorptivity, the equation will become A is equal to epsilon Cl, which is the Beer's-Lambert's law. So according to this, we can say that the absorbance is directly proportional to concentration and the thickness of the absorbing media. Now, for TYBSc, we are going to learn the atomic spectroscopy. Now, since the name suggests, atomic spectroscopy is related to the atom. So, there are two spectroscopy we are going to learn. First is emission spectroscopy. This emission spectroscopy is also called as a flame emission spectroscopy. Definitely we'll discuss it later in detail. And the second spectroscopy, that is absorption spectroscopy. Now, in the absorption spectra, we are going to learn the atomic absorption spectroscopy. Now, when any atom subjected to flame or thermal energy is subjected to any atom, the electronic transition takes place. Okay, this electronic transition can be shown by energy level diagram. So let us discuss the energy level diagram for sodium. Now, the outermost energy orbital of sodium is 3s energy orbital, and the higher energy orbitals are 3p energy orbital, 4p energy orbital, and 5p energy orbital. When this sodium is subjected to thermal energy, the electronic transition takes place. What are the possible electronic transition? Let us see. First possible electronic transition is from 3s to 3p, means electron get excited from 3s energy level to 3p energy level. Then the electron come back from 3p energy level to 3s energy level. This is called as an emission of radiation, and this absorption and emission takes place at 589 nanometer or 589.6 nanometer. Similarly, another possible transition is 3s to 4p electronic transition and emission from 4p to 3s energy level, and this absorption and emission takes place at 330 nanometer. And the last possible transition is from 3s to 5p energy level and re-emission from 5p to 3s energy level. And this transition takes place at 285.28 nanometer. But out of these three possible transitions, the most intense transition is the transition from 3s to 3p energy level and emission from 3p to 3s energy level, which takes place at 589 nanometer or 589.6 nanometer. So, which is the characteristics for sodium. Similarly, we can discuss the energy level diagram for potassium. Now, the energy levels for potassium is 4s energy level, the outermost energy level is 4s energy level, and higher energy level is 4p energy level, 5p energy level, and 4d energy level. Now in this diagram we can see that the 5p energy level come before 4d because it is having a lower energy than the 4d energy level. Now the possible transitions are 4s energy level to 4p energy level, while re-emission from 4p energy level to 4s energy level, which takes place at 767 nanometer or 769 nanometer. The, the another absorption and re-emission takes place at 404 nanometer from 4s to 5p and from 5p to 4s. And the last possible transition is from 4s energy level to 4d energy level and re-emission from 4d energy level to 4s energy level. And this absorption and re-emission takes place at 694 nanometer. But the most intense transition is at 767 nanometer 169 nanometer. This is all about this video. In the next video, we'll discuss the basic principle of flame emission spectroscopy. Till then, goodbye to all of you.